Hello. In the previous lecture, the concept of transactions in Bitcoin and after that Ethereum was discussed. As you know, there are some differences in the structure of transactions. However, in each transaction, there are common information like sender's wallet address, sender's public key, recipient address, the amount of money which want to be transferred, the fee which is considered by the miners, and something like this. Another important thing is that how these transactions are verified. As you know, in blockchain, after creating a transaction by a node, that node broadcasts the transaction through network. So all the nodes in the network will receive the transaction. So what if in this middle one node changes some part of the transaction and resend the transaction to other nodes? For example, suppose that Alice sent some money to Bob. What if a middle node changed the name of Bob with his or her name? The answer is transaction verification prevents other nodes to doing so. In fact, in this lecture, we are learning how to verify transactions, by which mechanisms different nodes can verify a transaction to being sure about who is the sender. In fact, how other nodes can check the authority of the sender, and also how they can check that other information like the amount, the recipient address, everything is correct. So in this lecture, at first, we learned about Bitcoin, and then we will talk about Ethereum. And in the next lecture, I will show you how in Python, how we can verify different transactions using digital signatures. So let's see a video about how verification is done in Bitcoin.
In this lecture, we're going to learn about verification. It's a kind of abstract thing. We're going to learn about what the verification things are you need to do, what it is you need to verify, and we're going to do a sort of abstract version of how you do this. We're not going to go into particular coins or the maths. That all comes later, okay? So let's start, okay? We're going to start with the task of verifying transactions. Right, here's a problem. How do we know that Alice initiated a transaction? This is supposed to be a transaction sending Bitcoin from Alice to Bob. How do we know that Alice is the one who actually initiated the transaction? How later, and this related question, how do we stop Alice from later saying, you know what, that wasn't me that said that? You want to be able to say, yes, it was, I've got proof. And the way you get your proof is Alice signs the whole transaction using a digital signature. So we can point to the digital signature and say, only you can have signed this. Okay. Right, here's another problem. How do we know that Bob receives the transaction? How do we know it's Bob? So let me just change this wording slightly because I'll make it more accurate, certainly from a Bitcoin point of view, which is somebody's going to later spend the money from that transaction. How do we make sure it's only Bob who can do it? And it comes from the fact that the address it goes to is the hash of his public key, and he just has to prove that that's his public key he's got the hash to. Here's another point, money availability. How do we know that Alice ever had the money? How do we know that we're not creating money during this transaction? I'm not sure that's still the money availability question, but it's certainly related. And thirdly, and most complicatedly, how do we know that Alice is not double spending the money? So what does that mean? That means Alice might want to buy a Tesla and also give Bob money. She wants to do that with the same money, sneakily or by accident. And she does it at exactly the same time. So if the Tesla dealer and Bob both check that Alice has the money, they'll both find out she has. And they'll say, sure, right? Or they might say, sure. That's the hardest thing to solve. And that's really what the blockchain is all about, how to solve that problem. We'll learn more about that a bit in this topic, but more later. Okay, so let's look at digital signatures. I said that she signs it. I've already told you that Alice signs with a digital signature. I'll say a little bit more about a digital signature. So remember, Alice has a public key and a private key, which I'm calling a secret key, just so they have different initials, right? Okay, so I've got a public key and a secret key, Alice has, and I'm going to specify two functions, sig and verify. I'm not going to say how they're defined, and we'll talk about how they're defined later, but I'm going to just tell you what properties they need to have. It's sort of a specification of the functions, not the functions themselves. So sig takes two inputs and returns another output. They're all strings. And what it's going to be used for is Alice is going to use this function sig with her secret key and the transaction, whatever the description of the transaction is. And Alice uses this one, and that provides a string, which we're calling a sig string. It's essentially a signature. But notice, first of all, that involves her private key. She needs her private key to do this. She's the only one who can do this. And secondly, it's got the transaction involved, not just the secret key. Now, this is different from a signature as you might be used to, right? My signature is my signature. It's not a different signature for every contract I sign. It's the same signature. And that's a danger, right? Because as soon as somebody has my signature once, they can copy it and use it to sign all sorts of things as me. And that's not great, right? From a point of view of security. That's why this signature isn't just a signature based on her secret key. It's based on her secret key and the transaction. She has a different signature for every transaction, every message. It's a different signature. So that knowing her signature for one thing doesn't give you any information about what her signature is for another thing. So having received something signed doesn't mean you know how to be her. Okay, right. So, right. Remember I said there were two functions. Sig was the one that took the secret key and the transaction, returned a new string, which is essentially her signature. Verify is the one we look at the secret key and the signature and we check that it's what we want it to be. Okay, so verify takes the public key, the transaction, and a string, and it returns a Boolean. So Boolean's either true or false, and it's true if and only if the string, the last input, is equal to applying that signature function not on PK, but on SK. On the SK, the secret key associated with the PK and the transaction trans. Okay, so that's Okay, that's another function, and Bob uses this one, and he gets a Boolean. And if it's a Boolean, he doesn't get a true Boolean, then he says forget it. If he gets a true Boolean, then he feels happy. Okay. Notice that he does not need to know Alice's secret key to do this. He just needs to know her public key and the transaction. Okay. And the maths does the rest. So the maths does the association of the secret key to the public key and checks the verification. We'll look at that maths for public key cases in, I think, 2 or 3 lectures from now. Then we've got the right address. How are we going to find out that it's Bob who's going to spend the money? Bob is going to need to establish that he has the secret key associated with the public key that Alice has used in the transaction. That's the destination, okay? Right, the destination, remember, is a hash of a public key. Bob has to show that he's got that public key. He's got the secret key associated with that public key. Everybody might have the public key. Knowing he has the public key doesn't tell you anything. He has to show he's got the secret key or private key associated with it. Money availability in whatever units we need some way of counting the money before and after, right? Okay, that's it for this lecture. And I'll see you in the next lecture. The next lecture is going to be about how this plays out in Bitcoin. Okay, see you there. Okay, we're about to talk about verification of transactions in Bitcoin. We talked about transaction verification in general, so about Bitcoin. So we remember there's 2 sorts of things we're going to verify. One is we're going to verify that the identities are right. So we're going to make sure that Alice is the person sending it and Bob's the right person who's going to receive it. That's what we're going to talk about in this lecture. The next lecture we're going to talk about how we know Alice has the money to begin with. Okay, so those are the 2 things we're going to verify. Well, I guess there are 3 things. And so we're going to go and do that now. So this is, as I say, there's 2 lectures about the verification of Bitcoin. There's this one about the identities and the second one about how we know she can afford it. So let's go on. The verification of Bitcoin transactions identities. That's what we're going to talk about in this lecture. So Alice wants to send Bob a Bitcoin. Yeah? So there's 2 parts involved. Alice creates an output. And the output's going to have money associated with it, Bitcoin associated with it, with a lock, essentially, saying only under certain circumstances can somebody spend this money. Spend is a big word in Bitcoin. So, because remember, the whole thing's transactions, nothing's really sitting in accounts. So we've got this output is called an unspent output until it's spent. While it's an unspent output, that's the equivalent of being in somebody's account. That's the nearest thing we have to bank money in the bank. So Alice creates an unspent output. The only person who can spend it is Bob in this case. That's not always the case. It's almost always the case. As I said in the last lecture or some time ago, you could have more complicated things here that say, well, I need any of these 3 people can spend it, for example, or something like that. But usually it's just one address that spends it, and we're going to go through in detail how that looks. So let's go with it. Okay, so Alice creates an unspent output, and then to spend it, Bob creates an input, and the input is going to have in it the information to prove that Bob is a person who could spend the output. So again, and then he makes a transaction later that spends that output, and that's what happens. So that is what happens with these things. And he might, when he does that, he may well, and quite frequently is the case, he would make an output that has somebody else, say Charlie, as the recipient of some of the money, and himself as some of the recipient of some of the money as well. So he would then get, there'd be till he spends that, it's an unspent output. So there'd be two outputs then, one for Charlie, one for Bob, and the one for Bob is unspent until he spends it. So you might be, when you spend outputs, they might be outputs that you'd sent yourself. Right. So spending's a big thing. Remember, we've got this chain of transactions, and it's about spending Bitcoins through these transactions. So how does Alice create an output? She collects information. One important bit is she says where she got the money from. That shouldn't say from, that should say from, but you've got the idea. Where did she get the money from? And that is an unspent output, or she's now spending. So that TXID V out that's on that slide is an unspent output, right? That's an unspent output, and what she's doing now is spending it. So when she makes this output, she's spending that output. So, and that is an output. TXID is the name of a transaction ID. V out is one of the outputs on that transition. So it's transaction. It's a 0 or 1 or 2 or something like that, right? Okay. So that's an unspent output that she's now spending. So she puts in various other things as well, and she bundles it all up in one description, which she then signs with her secret key. This is really important because Alice signs with a secret key, and then anybody with her public key can check she signed it. Okay? And it doesn't even mean they can see that much. This is to kind of verify stuff we were talking about before, right? Okay, so. Okay, Alice signs it, so we know it's Alice. Anybody can check this, and in fact they do. Right? Okay, so that's something that gets verified. So Alice arranges, but she's going to arrange the output so that only Bob can spend it. So she's making a new unspent output, and only Bob will be able to spend it. And Bob spending it is the next transaction. Okay? Right. And as I say, it's an unspent transaction until Bob spends, and I put output until Bob spends it. So this is an output. It's got the most important thing here is the PK script in the upper left-hand corner, which we're going to go through in quite detail. That's a little scripting language that Bitcoin uses, and we're going to see that what it does is it gives some commands to a stack. I'll talk about that as well. And we've got the sense of how much money is there, etc. So Bob's input, and the most important thing in this is that he's got a SIG script. And that SIG script is two numbers. Two big numbers, right? Okay. Strings, numbers, what have you. So that's the most important thing here. So what is that SIG script? It says there's two strings. Let's go back for a second. The one on top is his public key, and the one on the bottom is his signature. So we've got a signature and a public key. Okay? Bob's public key, Bob's signature. That's what that SIG script is. Oops, that's kind of wrong. Oops. Okay. The PK script on the output is this lock. On Alice's output, there's a PK script, which is a lock that only can be spent if you've got the right key. The SIG script is that key. Okay? The unlocking only happens when Bob wants to spend the output. So the unlocking only happens when Bob is spending the output in the next transaction. Okay, PK script is a program. It's a little program, and it manipulates a stack. So just to remind you, those of you who you probably mostly all know what a stack is, but just to remind you if you don't know, a stack is a standard computer science data type. It's like the metaphor is like a stack of dishes or a stack of books, but a stack of dishes is how I learned it. And so the point of it being a stack is when you want something from it, when you're dealing with it, you always start with the thing on top, right? You don't go in, we need a dish, and you've got a stack of dishes, you don't start from the middle, you take the one from the top. So it's always dealing with the thing on top. And then you've got some standard operations. Push, put something on top of the stack. Pop, take something off the stack. So that's push and pop, sort of two main operations. Dupe is an operation we'll be seeing. What it does is it takes the top of the stack, duplicates it, stands for duplication, and puts it on top of that. So it puts it on top of the stack as was. Equals another thing, or some version of equal. We'll look at the two things on top and see if they're the same. If they are, it will get rid of them both, it'll pop them both, and we'll just get on. If they're not, cause some error. Okay. Now, this is the PK script, except instead of the middle bit, I'm telling you what it is. If you look at the PK script on the output I showed you, it doesn't. It's just a big string. But what that string is it's the address that Alice is meaning to send this to. Okay, can be different from that, but that's what it generally is. Okay, so the stack just starts as the SIG script. We've seen the SIG script has got the public key on top of the signature. And then the first command on that was op-dupe. It duplicates the top thing and makes another copy. Okay. The next one is a hash, and a hash 160 just says what hash it is. So look at this. This is what it was before the hash. What that does is it always operates on the top thing. It hashes the top thing. Right? So we've now hashed the top thing. And now intended address. So what that command does, that's just and a string is, it says essentially push this string onto this stack. That's exactly what it says. Push this string onto the stack, which is what it does. So now the stack has an extra thing on it, which is the intended address. Okay. This is a bigger slide. Okay, so it's now looking at equal verify, which is I just used equal a few slides ago. This checks if the first two elements are the same. If the first two elements are the same, it pops them off. If the first elements are not the same, then you fail, and that's the end of this, right? So what are the two elements here? They're the intended address and the hash of Bob's public key. So the question is are they the same? If they are the same, we just get rid of them and keep going. So let's assume they are the same. So we keep going, and we get this. The stack is now gone back down to where it started. Actually, it's just the public key and the signature. Yeah. And then the last thing is this check sig. So it's got two inputs now. It's got two things on the stack. And the check sig, what it does is it is a function of those two things. So it's a function of two variables, so it takes those two from the top. And what it does is it takes the public key and the signature, and it is our old friend, the verify function we talked about, with the transaction sort of buried within it. So it's essentially this, that it returns a Boolean that's true if and only if the string at the right is the signature associated with the public key on the left, right? Remember, that's what we did we talked about this before, right? Okay, so that's what's happening here. So this check sig is that verify function essentially that we talked about before. You knew it would come up someplace. So what is this done? What's PK sig done? It's done two things. It's checked that the public key in SIG script is associated with the intended address. Okay? Remember, 6 script has a public key and a signature. So check that public key is the one that's associated with the address that Alice wants the money to go to. The second thing is, it checks that Bob has the secret key associated with the public key. That's what that check did. That's what that last bit did. The thing that's with the verify. It checked that Bob, because Bob could put this on his input, Bob has that secret key associated with the public key. We know that. So Bob, it's not just that it's going to the right place. We know that Bob knows it's going to the right place. Okay? And that's it. So the next lecture is going to be about how we know Alice has the money. Okay? So, see you then. We're about to start the second part of the verification of Bitcoin. It's actually considerably less involved than the last lecture. We've had the hardest part of the Bitcoin transaction verification already done. This is quite a bit simpler. I think it's probably the end of the hard part of this particular topic. So I want to do some more maths with you, but I think it might be next topic. So let's go on and do this. Okay, so verification of unspent transactions, of Bitcoin transactions to unspent transactions. We've spoken about unspent transactions before. Unspent transactions are a big thing in Bitcoin. Okay, so where do we leave Alice and Bob? Bob has an input. The input has a SIG script. The SIG script shows that he's Bob, essentially. It's a signature. Alice has an output with a PK script, which is sometimes called a script pub key. I think actually maybe more frequently called a script pub key, but they're the same thing. And that's a sort of lock. So Alice has her output locked so that only Bob, who's got a SIG script, I notice I've misspelled with, but I think you can deal with that. Okay, Alice has locked her output so that only Bob can spend it. That's what we just seen, right? That's what happened in the loss. We went through the PK script and put that into the stack. The PK script ensures that Bob can spend the output. In fact, it ensures that Bob's the only one who can spend the output. But until he does, Alice's output is unspent. Until Bob spends it, it's unspent. It's kind of tautological, but it actually means something because unspent transaction outputs are an important thing. Until Bob comes along and spends that output, it's an unspent transaction output, which is the symbol for that is, or the acronym for that, or whatever it is UTXO. So unspent is U, TX is transaction, O is output. So UTXO is an unspent transaction output. Until Bob spends it, that's what it is. It's sitting sort of as an output on Alice's transaction, but it's only available to Bob. So it's really kind of Bob's, isn't it? And that's the point. It's unspent transaction outputs are the equivalent of money in the bank. It's as near as we get to talking about money in the bank. It's the unspent transactions outputs. And so that really belongs to Bob, that unspent transaction output, because he's the only one who can spend it. So that's Bitcoin. Bitcoin keeps track of the full set of unspent transaction outputs at all times. So when Alice comes along to spend money, she says, first of all, where she's getting that money from. I've said this several times now. So she gives the address of an output. So she says transition, whatever, transition 354, and the second output of that transition. So it's a pair. It's a name of a transition, a TXID, and which output it is of that transition, and the out. Okay. So that's used to make sure that Alice has the money she's spending. She says, okay, this is the UTXO I'm spending in this transaction. She can only spend UTXOs. So the Bitcoin checks that it's a UTXO. When I say Bitcoin, I don't mean anything central. I mean the Bitcoin community, the Bitcoin network. Anybody who wants to know that they can put this on a block, for example, which could check that when Alice says she's spending an unspent transaction output, they could check that it's an unspent transaction output. That's part of what happens in the checking that Alice has the money. Okay, got that? That's really important. That's really what it is, what happens, the way they check that Alice has the money. You check that it's actually, there is a UTXO and that it belongs to Alice. Right, remember, I talked about the last one belonging to Bob, but the UTXO really belongs to the person who can unlock it. Okay, so checkers can check that the money is unspent by checking if it's in UTXO when accepting a transaction. This does not solve the double spending problem. Remember, the double spending problem is, suppose Alice tries to spend that money. We like Alice, so it's probably a mistake. But suppose she tries to spend that same UTXO twice to two different people at the same time, just as an oversight, right? Could be on purpose. In any case, that if she did that, and Bob and Charlie were both presented with I'm going to give you this UTXO or part of this UTXO, whatever, they would both say sure, why not? Okay, so the system would do that. So we're going to learn about how the blockchain stops that. That's what the blockchain is set up to do. The blockchain and the mining process, and consensus process. So we'll talk about the blockchain in topic 5. We'll talk about the consensus and mining in topic 6. Right? Okay. So we will get to the double. We're not dodging the double spending problem. I'm just reminding you now we haven't solved it yet. And the other thing to note is the other thing I wanted to talk about. I mentioned that we wanted to do is that money isn't created in these transactions. So you've got, in these transactions, you've got outputs and you've got inputs. You've got those unspent transactions there, and you've got this, you've got this is the input, right? This is what it's going to actually be, go into the next thing. And so this is the input, these are the outputs, okay? So the sum of all the outputs has to be less than or equal to the sum of the inputs. That's the point about it, money not being created. Okay, so you might think why it should be equal, and I don't think I've talked about this before. The difference is a fee. Now the fee isn't fixed, you choose your fee yourself. But the point of having a fee is that the fee goes to the, and I'm getting a little bit ahead of us here, but the fee goes to the person who's making a block for the blockchain, and you're trying to incentivize that person to put your transaction in his block. That's what's happening. Okay? Okay. Remember, we talked about this with Ethereum as well. We talked about gas and prices. But this is a little bit different. This is just what's left over from the transaction. That turns out to be a fee. The other thing is to note, I've said I think several times, is that frequently you send a transaction to yourself. But so more on this, and when we're talking about miners in chapter 6, into topic 6. But if I look at this example, and this shows how seriously I take this. This is a hard sum to do. Look at that output. Look at those inputs. Sorry, the other way around. Look at these outputs and that input. I added those two up. That's not that easy. I couldn't cut and paste because anyway, never mind. I did that and I found that the difference between the outputs and inputs in this particular case is that number there. And that's the fee that goes to the miner. And so the only transactions where money is created are what are called coin-based transactions. COINBASE, coin-based transactions. And they're easy to spot. They look quite different from anything else. And those only happen when you make a new block for blockchain. So again, I'm getting ahead of myself. Some of you will know that there's a company called Coinbase, and it's taken its name from these Coinbase transactions. Okay, and that's all I'm going to say about Bitcoin transactions now. I'm going to move on to verifying transactions in Ethereum and in Zimcoin, which is going to be quite similar to Ethereum, and they're both easier than this. Okay, so see you in the next lecture. Okay, we're leaving the world of Bitcoin behind for now, and we're going into the world of Ethereum. And then from Ethereum to Zimcoin, and which is much more like Ethereum in this regard than it is like Bitcoin. So we're going to look at this, and this is much easier than it is in Bitcoin because we have accounts instead of just transactions. Okay, verification of Ethereum transactions. So, right. So the point here is that we've got accounts. We have two kinds of accounts, remember? Let's just stick at the moment to thinking about the easy accounts, what are called external accounts. So external accounts really just have money in them and an owner and unknowns, which we'll talk about. So the accounts have states, okay? The state of an account is how much money is in it. The state of the network is the state of all the accounts. So there's a sense of state of the whole network, and that says how much money there is in each account. And the nodes know about that. Besides that, each account has a nonce. Now, nonce means something that's only used once. So this is a random sort of thing that's only used once. And in Ethereum, the nonce is updated after each transaction. And the reason for that is simple. I'm going to sign this transaction. So if I were giving Alice money, Ether, and I signed something saying I'm giving Alice 3 Ether, and if all that was involved in that signature was me, 3 Ether, and Alice, then Alice could use that again if she weren't scrupulous and take 3 Ether from me every day. But what stops that from happening is the nonce, which changes, means that my signature of that transaction now is not useful to sign anything else. So there's no use in knowing that. It's not going to let you do anything else. Okay, we also have contract accounts, which have smart contracts that execute every time a message is received. And as I talked about external accounts. How do you know the transaction is actually authorized by the owner of the account? Well, the sender signs the whole transaction with a secret key, and the whole transaction, as I said, includes the nonce. So the signature can only be used once, but all nodes of the network can check to see that using that person's public key, the owner's public key, can check that it's actually been signed. Again, using that verify functions we talked about some time ago. Okay, the nodes of the network also know the state of the network, so they can check that the sender's balance is at least as large as the payment plus a fee. So they can check that it's all quite laid out. It's quite simple to check that the money is there. Okay, how are we going to adopt this for our coin? Okay, so each transaction will have the sender's public key and sender's signature. The addresses will be the hashes of the public key, and we will keep track, something like a state, we're going to keep track of a sort of map of addresses to balances, sort of a graph with addresses, balances, and, or even a table, right, with addresses and balances on it. Okay, the keys will be made using elliptic curve digital signature algorithm, and we will talk about that, I think, to some extent. But you won't need to actually implement that. You can just use the Python implementation of that. So you'll have all of this in more detail by the time you have to implement it, which soon. And that's it for this. Okay, bye for now.
Okay, that was some useful information about how the transactions are verified in Bitcoin and in Ethereum. In the next lecture, I will show you how we can implement these concepts, verifying the transaction using digital signatures through Python codes. So